Hello and welcome back to Mr. Powers Teaches Algebra. We're doing algebra. And we've been working on binomial theorem. So it's kind of like the third part. So this is a trilogy of the binomial theorem. And I've loosely talked about here the Pascal's triangle, binomial expansions, how the Pascal's triangle, they're kind of giving us the coefficients on the terms in a binomial expansion. But I also related these binomial expansions to finding all possible outcomes when choosing between two different things, you know, 3 times or 2 times or 4 times. So, we saw that relationship. And so then it seems as though, because we can do that, we can use this formula for combinations as our coefficients in a binomial expansion. So then there must be a link, or at least it looks like there is. Maybe it breaks down at some point, but it looks like there is a link between the binomial theorem, for finding the coefficients in a binomial expansion. There's a link between those coefficients, which are combination notation. We can use the combinations here. Those and the values in our Pascal's triangle. So let's connect those up. We can easily do that using, I think, a kind of a induction proof. But we're going to do it more intuitively, I think. So let's start with a Pascal's triangle. How do we get Pascal's triangle? To get Pascal's triangle, it's pretty easy. All we got to do is start with 1. So we make a triangle, we start with 1. And I think we'll probably be fine. We'll start here. And then the second time we go another 1 and a 1. And then now the third one, the third row, is going to be, again, 1's on the edge. We always got 1's on the edge. But to get the one in between here, right, that's below it and between these two, we're going to say that's a 2. So in other words, these two add up to get this term. And we're going to keep that going. So it's 1. 1 plus 2 is 3. 2 plus 1 is 3. And then we have the 1 here. Okay? And we just can continue this pattern on and on and on. And that's how we get our Pascal's triangle. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we keep doing that. We can do it one more time. 1, so 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then 1 out here. Okay. Now, so we're going to make a couple of inferences here. First off, we can easily show that each of these are working, that we are getting our same values as in our choose or combination notation. So if we, let's say here, it's kind of silly, but 0 choose 0. This is row 0, by the way, right? Row 0, row 1, row 2, and so on. 0 choose 0. So then this one could be 1 choose 0. Whoops. 1 choose 0. And this would be 1 choose 1. 1 choose 1 right there. And actually, let's switch this notation up, or the color up a little bit. And then again, this could be here for row 2. This could be 2 choose 0. There's one way to choose nothing out of 2. This guy could be 2 choose 1. That's 2. and then 2 choose 2 is that 1 right there. There's only one way to pick 2 things out of 2 things. Okay? And so we're getting all these connections. We can see it there. And we can go on and prove it for this way. But could we really show that it keeps working forever and ever? And my claim is you can, because how do we get new rows? How do you get new rows of Pascal's triangle? Well, we already talked about that. You add these two up to get the next one. 10 plus 10 is 20. 5 plus 10 is 15. 5 plus 1 is 6. That's how we're getting it, right? So if I can show that this thing, if I can show right here, and we call this Pascal's identity, if we can show this is true, then I can make that link. I can say, you know what? All these values in Pascal's triangle, they are getting me all my values for choose notation, for combinations. They're getting me every way I can do, like say here, row 3, 3 choose 1, 3 choose 2, 3 choose 3. It's giving me all the values for combinations. Okay? We can show that. So, because that's literally what's going on here, right? This plus this equals this. So is that the same thing first? Let's see. So this would be 1, 2, choose 0, 1, 2, 3. So this is 5, choose 3, plus right here, this guy is 5, choose 4. Yep. Does that equal this? And what would this be? This would be 6, choose 0, 1, 2, 3, 4. 6, choose 4. Right? That's exactly what's going on. So is that the same pattern as this right here? I kind of have it flipped around on us, but n choose r minus 1. That's n choose r. R in this case is going to be 4. So n choose r minus 1 plus n choose r. So one more. Yep. Does that equal n plus 1? So instead of 5, it's 6 here. Choose r. Chooses yes. That's exactly what's happening. So if I can show this identity works, then I've proven that Pascal's triangle is getting me all these values. Great. Let's see it. Let's see if we can prove this. There. So that's my thinking. That's going to be my proof. If this identity is true, then Pascal's triangle does in fact give me these values for choose notation. It gets you combinations, tells you how many ways there are to pick a number of elements out of another set of elements. Okay, so let's see here. Let's go ahead and prove this. So first thing to notice here, and actually I'm going to switch it around. Oh, well, no, I'm not. It doesn't matter. So let's start with the right side and see if it adds up to the left, right? So let's see if we can get this. What is the left side here? Well, remember what combination notation is, right? So just as a little reminder here, n choose r or NCR, however you want to do it, is really just n factorial over n minus r factorial times r factorial. Okay? Let me see here. Okay. Everything's looking good. That is what this means, right? So let's see what happens if we rewrite these in factorial, and let's see if we can end up with the left-hand side. Let's see if these are, in fact, the same. So this guy here is going to be n factorial over n minus r minus 1 factorial times r minus 1 factorial plus n factorial over n minus r factorial times r factorial. Okay. We got to combine these. We want like terms on these. So let's see what we got. We got r minus 1 factorial, r minus 1 factorial. That's the same. Oh, no, I'm sorry. N minus r. Here we got r minus 1. So actually an r factorial. So I think if I multiply top and bottom here by r times r, we got r factorial, because r times r minus 1 factorial is r factorial. So that's going to get me the r factorial is the same. But to get n minus r factorial, that one's a little trickier. Let's go ahead and take a look at what we got so far. Give me 1 second here so you don't. Wow. Well, we'll work it out. I guess you could always fast forward. So n factorial times r, or I guess we would just write r times n factorial, whatever. So r times n factorial over, if we distribute this minus in here, what do we get? We get n minus r plus 1 factorial. Okay, that is going to make it a little bit more clear here what we got to do to get these the same. There we go. Times r minus 1 factorial. Well, actually, r times r minus 1 factorial is r factorial now. So now we have times r factorial plus n factorial over n minus r factorial r factorial. Okay, so this is n minus r plus 1. So if I subtract 1 from this, I'll get n minus r factorial. How do you subtract 1 from this? So, well, this is really, if we rewrite this, and I might be doing it kind of slow, but I think it's fine. It's going to be a long video. I could rewrite this still as r times n factorial, and this guy I could rewrite as n minus r plus 1 times n minus r factorial times r factorial. So what I did was I factored out the n minus r plus 1. The way factorials work, we can totally do that, because the n minus r plus 1 times n minus r times n minus r minus 1, and so on. That's what n minus r plus 1 factorial is. Plus, okay, and we still have n factorial over here over n minus r factorial, r factorial. Okay, we're getting there. Now, these, we can see the difference here. I got to do one more thing to get a common denominator. I got to multiply top and bottom on this fraction here by n minus r plus 1. So I got to say, hey, times n minus r plus 1 times n minus r plus 1. And now I have a common denominator, which is wonderful. It's amazing. So, okay, now we can combine like terms. So let's see here. And when we combine like terms, remember I split this up into 2 factors, and so I have the same 2 factors here. But really now they're both n minus r plus 1 factorial. So my denominator now is n minus r plus 1 factorial times r factorial. And my numerator is, well, we add these up. So it is r n factorial plus n factorial. Well, actually, let's put that other thing in front because we're going to do some factoring here. Plus n minus r plus 1. Yep, times n factorial. Okay. Well, I can factor that n factorial out. So let's do it in the numerator. So if I factor out the n minus the n factorial out, we would get, let's see here, r plus n minus r plus 1 times n factorial over n minus r plus 1 factorial, r factorial. Hang with me. We're almost there. We almost got this. Hey, guess what? R plus negative r is 0. So what this really is in the numerator now, and now we can finally, we're almost there, is n plus 1 times n factorial over n minus r plus 1 factorial r factorial. And remember what we're trying to get. We're trying to get n plus 1 factorial, or n plus 1 choose r. What is n plus 1 choose r? What is that? That's going to be n plus 1 factorial over n minus, n plus 1 minus r factorial times r factorial. That is what we're trying to get. That's what this is on the left side. Did we get that yet? Well, the numerator is n plus 1 factorial, because n plus 1 times n factorial is n plus 1 factorial. Okay, we got that. And then the numerator, n plus 1 minus r, n plus 1 minus r factorial. Yep, we did get that. That is exactly the same. I suppose we'll write it like this. N plus 1 minus r. N plus 1 minus r factorial r factorial. Okay. Well, guess what? Pascal's identity, this is true. And we just proved that it is, which means when we add two terms in our Pascal's triangle, to get the one down below it in the middle here, like 10 plus 5 is 15 or 10 plus 10 is 20, that is getting us the next row for our combination. It's getting us our next values for choose notation. So this does end up being 6 choose 1. It is the number of ways to pick one thing out of 6 things. This does end up being 6 choose 2. The number of ways to pick 2 things out of 6 things, and so on and so forth. It does work. So there we go. That's it. There's my proof. There's the connection, the long step-by-step showing of this. So hopefully that's useful. If you find it useful, great. Until next time, enjoy doing math.